Have you ever really stopped to think about what's going on inside your body when you're scuba diving? It's way more than just breathing. Today, we're going to take a deep dive, literally, into the invisible science that keeps us all safe underwater, the absolutely fascinating world of decompression theory.
So picture this. You're on a beautiful dive, you look at your gauge, and you've got tons of air left. But your dive computer is screaming at you, telling you it's time to head up. What gives? Well, the answer has nothing to do with the air in your tank. It's all about the gas that's already inside your body.
You see, the whole puzzle comes down to an invisible passenger that your body picks up the second you start to descend. It's a gas that's totally harmless on the surface, but becomes the single most important factor to manage under pressure. And that gas is nitrogen.
Okay, so the air in your tank, it's about 79% nitrogen. Up here on the surface, no big deal. You just breathe it in and out. But as you go deeper, the immense water pressure literally squeezes that nitrogen gas, forcing it to dissolve and soak into your body's tissues. The deeper you go and the longer you stay, the more of this stuff you absorb.
Now, here's where it gets really interesting. Your body doesn't soak up this nitrogen all at once like a single entity. To figure this out, scientists came up with a clever idea. They modeled the body as a collection of different compartments, and each one has its own unique speed for absorbing nitrogen.
Let's be really clear, though. These aren't literal physical boxes inside you. Compartments are just a theoretical way to represent how different types of tissue, like your blood, your bones, your muscles, all absorb and, just as importantly, release that dissolved nitrogen at their own pace.
You know, the best way to picture this is to think of sponges. Your blood, that's like a small, really porous sponge. It soaks up nitrogen super fast, but it also releases it just as quickly. Now, on the flip side, you have your bones. Think of those as a big, dense, heavy sponge. They take a really long time to get saturated, but boy, they also take a very long time to dry out.
And you've got this whole range in your body. You've got your fast compartments like blood, then medium ones like your brain and spinal cord, then slower tissues like skin and muscle, all the way down to the super slowpokes like your joints and bones. Basically, every single part of you is on its own unique timetable.
So, if every part of you is a different kind of sponge, how in the world do scientists measure their speed? Well, they put numbers to this whole process using two absolutely key concepts, half-times and m-values.
Okay, first up is the half-time. It's the core measurement, and it's pretty much what it sounds like. It's simply the time, in minutes, that it takes for a tissue to get 50% saturated, or halfway full, with nitrogen once you've settled at a new depth.
But here's the really crucial part to get. This saturation process isn't a straight line. Nope, it's exponential. So after one half-time, a tissue is 50% full. After a second half-time, it's 75% full. It actually takes a full 6 half-times before a tissue is considered completely on-gassed or saturated.
Let's make this real. Let's say a tissue has a 5-minute half-time, and you drop down to 18 meters. Okay, after 5 minutes, that tissue has absorbed nitrogen equal to 9 meters of pressure. After another 5 minutes, it soaks up half of what's left, and so on and so on.
And this all leads us to the single most critical concept. There is a limit. Every tissue compartment has what's called an M value. That's its maximum allowable pressure, its safety ceiling. If you surface with any tissue over its M value, that dissolved nitrogen can fizz out of solution and form dangerous bubbles, causing decompression sickness or DCS.
So those three big ideas, compartments, half-times, and m-values, they're not just abstract science. They are the absolute bedrock of every single tool divers have ever used to stay safe, from the old-school dive tables to the sleek computers we wear on our wrists today.
For decades, divers just used tables developed by the US Navy. But by the 80s, people realized that military dives, single, deep, heavy work dives, were a totally different ballgame from what recreational divers do. We do multiple, shallower dives a day on vacation. That realization led to the invention of the Recreational Dive Planner, the good old RDP.
And the differences are huge. The RDP uses a much more sophisticated model with 14 different tissue compartments instead of the Navy's 6. It also assumes you off-gas nitrogen faster, which makes it way better suited for someone on a dive trip doing 2 or 3 dives a day.
Which of course brings us to today. Most of us use dive computers, right? Well, they're running on these exact same principles. But the huge advantage is that a computer tracks your depth and time every single second. It doesn't force you to round up to the next box on a table. It gives you a much more accurate and usually longer no-stop dive time.
Okay, so we've covered a lot of science. How does all this theory actually translate into what we do on a dive? Well, it's the why behind all those simple, life-saving rules every single diver learns.
Let's start with a classic. This safety stop. We all do it, hopefully. But have you ever really thought about what's physically happening inside your body while you're just hovering there for 3 minutes?
That simple little pause at 5 meters is a crucial off-gassing window. It gives your fast sponges, remember tissues like your blood that soaked up nitrogen quickly, a chance to gently exhale that gas in a controlled way before you hit that huge pressure change right at the surface. It's a safety buffer that makes a massive difference.
And what about flying after diving? That 12-hour minimum wait is there for your slow sponges. It's protecting the tissues that take the longest time to release all that stored nitrogen. The waiting period makes sure they've had enough time to get back to normal before you go up to the low-pressure environment of an airplane cabin.
That deepest dive first rule, that's all about managing your nitrogen budget for the day. You hit your body with the biggest dose of nitrogen when your tissues are completely clean. Then, for your next dive, which is shallower, you're absorbing nitrogen at a much slower rate. It's just a smarter, more conservative way to dive.
So when you put this all together, you start to see that the rules of diving aren't just arbitrary. They're not just things people made up to be difficult. They are the real-world application of decades of science.
And that right there is the real takeaway. Knowing why you're doing a safety stop or why you wait to fly, it transforms you. You stop being someone who just follows a checklist and you become a diver who truly understands what's happening. That makes you smarter, more confident, and ultimately much safer.
But it's so important to remember that all of this, the compartments, the half times, the M values, it's still just a mathematical model. It's an incredibly smart model, but it's trying to describe wildly complex human biology. It's the best tool we have, but it's not perfect. Which really leaves us with a pretty cool question to think about. As our science and tech get even better, what new secrets are we going to uncover about the human body under pressure?